Good morning, good afternoon, and good evening. Today I'm going to talk about enhancing the performance of high viscosity friction reducers, or HVFRs, in brine. This is written by a few folks from Stefan Oilfield Solutions and from the University of Texas. I covered the objective and methodology together in this slide. The objective is the study explores and reports the use of surfactants to alleviate the loss of performance of HVFR fluids due to salinity in the mixed water. The methodology is that fracturing fluids were prepared in the lab by mixing HVFR concentrations between 2 to 8 gallons per 1,000 gallons without the surfactant formulations. The viscosities of the fluids were measured on TA measurements and DHR3 rheometers using a concentric cylinder geometry. Both anionic and cationic HVFRs were tested with various surfactants. Specifics of the test setup and everything are written in the paper, and they're not covered in this presentation, so I suggest you look at the paper to review those details. I'm going to go straight to the results and discussions, and this covers the viscosity measurements. This figure 1 illustrates the effect of salt on HVFR fluids by comparing the viscosities of fluids containing 6 GPT HVFR anionic and brines containing the increasing amounts of KCl. At a very small amount of KCl caused nearly a 5-fold decrease in viscosity at the lower end of the shear rate range. At high KCl concentrations, the deterioration in viscosity was even more pronounced, to the point that 5 and 10% KCl, the viscosities were nearly water-like. This chart is just the confirmation of existing knowledge and conventional wisdom of that of HVFR fluids are rendered ineffective in the presence of even small amounts of salts. Now this is figure 2. Shows the viscosity in 3 sets of fluids preparing the 2, 4, and 6 GPT. One set of fluids was prepared without any surfactant, while other contained 10% surfactant formulation relative to HVFR loading. The control fluids nearly had water-like viscosities. In addition, these fluids displayed Newtonian rheology. On the other hand, the HVFR fluids containing surfactant had much higher viscosities in all cases and non-Newtonian or shear thinning rheology at 4 and 6 GPT. The viscosity increase was especially significant at low shear rates. In polymer solutions, non-Newtonian rheology indicates structure formation by a swelling and enlargement of polymer chains. On the other hand, Newtonian rheology indicates the lack of structure due to the polymer chains not having swelled enough to interact with one another. Now I'll talk more about Table 1 and Figure 3, which are on the future slides. So even though surfactant formulation resulted in significant viscosity enhancement at 10% KCl, produced in recycled waters contain significant amount of divalent cations, which are known to cause more severe deterioration of friction reducer performance than monovalent ions. The effect of divalent cations on HVFR performance and the ability of surfactants to alleviate the lost performance were investigated by using a series of model solutions of sodium chloride and calcium chloride. The compositions of the model solutions are listed in Table 1. The Figure 3 shows the viscosity of 6 GPT in the model of NaCa brines with and without surfactant formulation. As expected, there was no difference in viscosity between the fluids and without surfactant and tap water. On the other hand, the surfactant provided significant viscosity increases in all brines. The enhancement in viscosity has the highest at intermediate TDS levels. This is illustrated in the inset in the figure, where the ratio of boosted viscosity to the control viscosity at 10 inverse seconds is plotted against TDS. At low TDS, there is relatively moderate reduction in viscosity of the control fluid compared to the analogous freshwater fluid, and therefore there was limited room for viscosity enhancement. At intermediate TDS levels, there was severe reduction in viscosity of control fluid and surfactant to the most significant impact on viscosity in the TDS range. Finally, the highest TDS in the salinity was so high and the brine was such a poor solvent in the polymer that the viscosity boost was diminished. These results confirm that the surfactant results are significant enhancement in HVFR fluid viscosity in brines containing divalent cations. This is Table 1 showing the composition of the model sodium and calcium brines, and this shows you the details of Figure 3. So viscosities of fluids prepared with 6 GPT HVFR anionic with or without surfactant formulation at 25 degrees C. The inset shows the ratio of the boost to control viscosities as a function of total dissolved solids. The paper also covers proppant settlement versus your HVFR, so the height of settled proppant as a function of time, control for HVFR fluid, and the HVFR fluid with surfactant. So the addition of surfactant resulted in a significantly lower rate of proppant settling compared to the control fluid. So this figure 8 shows the friction pressure data in dimensionless form for two fluids, slick water fluid containing 0.5 GPT and 6 GPT, plus this 0.6 GPT of surfactant formulation in 5% KCl. Since the viscosities of these fluids are significantly different, it is more meaningful to compare the fanning friction factors and Reynolds numbers instead of the raw pressure differential flow rate data. This figure 8 illustrates that two fluids display nearly identical behavior, confirming that the HVFR fluid with their surfactant formulation continues to provide adequate friction reduction after accounting for higher viscosity compared to slick water fluid. The paper covers several conclusions. As expected, the salinity resulted in a significant reduction-like performance of HVFR fluids. In the extreme case, the fluid viscosities were nearly water-like. The surfactant formulation used in the study resulted in significant viscosity enhancement of HVFR fluids in model brines, as well as brines that mimic the field-produced water compositions. At low shear rates, up to 10-fold viscosity increase was observed. The magnitude of viscosity increase was dependent upon the composition of brines. The viscosity enhancement was achieved in both anionic and cationic HVFR fluids. The increase of viscosity with the use of surfactant resulted in the HVFR fluid displaying superior proppant transport. In tests performed in a rectangular slot, the fluids with the surfactant formulation transported nearly 4 times as much as the proppant through the slot. The use of surfactant formulation to enhance fluid viscosity can enable operators to use recycled and produced water for hydraulic fracturing, resulting in a less expensive and more sustainable process. Additionally, the surfactant formulation can reduce the amount of HVFR required to achieve a certain viscosity in brine, which is likely to reduce the likelihood and potential severity of formation damage. Flow loop measurements confirmed with HVFR fluids in brine containing the surfactant formulation provide as much friction reduction as slick water fluid on a dimensionless basis. Thanks so much for listening to this presentation. As usual, please be sure to like this video, subscribe so you can get more content in oil and gas and professional development topics, and please be sure to comment on the video below on the YouTube platform so I can incorporate your feedback into future videos. Please be sure to hit that notification bell when you do subscribe, because I upload every Friday and every Sunday. Every Friday is a professional development topic, and every Sunday is a technical review. Once again, thanks so much for listening to this presentation, and I'll see you in the next one.